Calculating the demand load for cooking equipment involves understanding the National Electrical Code, specifically Table 220.55 and its associated notes. This is applicable to single-family dwellings with multiple cooking appliances. The goal is to determine the appropriate electrical load to account for these appliances. Firstly, let's consider the scenario where we have a 12 kilowatt cooktop, a 10 kilowatt oven, and a 9 kilowatt oven, all operating at 240 volt single phase. Several methods exist for calculating the demand load, each with its own rationale. One approach, sometimes favored, assumes all appliances run simultaneously. In this case, the demand load is determined by the lowest rated appliance, which is the 9 kilowatt oven. This yields a demand load of 9 kilowatts. However, this approach may not accurately reflect real-world usage patterns. A second method utilizes the 100% demand factor for cooking appliances as specified in Table 220.55, Note 4. This method often leads to selecting the highest rated appliance as the demand load. In this example, the 12 kilowatt cooktop would be chosen, resulting in a demand load of 12 kilowatts. Note 4, however, may not always be applicable depending on the specifics of the installation. A third method involves summing the individual appliance demand loads calculated in accordance with Table 220.55, Note 1. Note 1 states that the demand factor is 100% for the first 12 kilowatts of cooking appliance demand and 50% for the remaining demand. Applying this to our example, we have a total connected load of 12 kilowatts plus 10 kilowatts plus 9 kilowatts, which equals 31 kilowatts. The demand load calculation would then be 12 kilowatts plus 50% of the remaining 19 kilowatts. 19 kilowatts times 0.5 equals 9.5 kilowatts. Then add 12 kilowatts plus 9.5 kilowatts, which gives a total demand load of 21.5 kilowatts. This method takes into account that not all appliances will operate at their maximum rating simultaneously. A fourth approach introduces a diversity factor, a multiplier used to adjust demand loads to account for the fact that not all appliances will operate simultaneously. For example, summing the individual appliance demand loads, which we know as 31 kilowatts, and multiplying by a diversity factor of, say, 1.2. This gives a demand load of 37.2 kilowatts. This method is useful when the expected usage patterns are known and can be quantified. When choosing the most appropriate demand load to use, it's crucial to consider the specific requirements of the electrical system and the intended operating conditions. Factors such as the size of the service entrance, the capacity of the panel board, and the expected usage patterns of the cooking appliances must be taken into account. For instance, if the service entrance is undersized, using a lower demand load may be necessary to avoid overloading the system. Conversely, if the cooking appliances are expected to be used frequently and simultaneously, a higher demand load may be warranted. NEC Table 220.55 provides guidance on calculating the demand load for household cooking appliances. The table offers various columns and notes that address different scenarios based on the number and rating of the appliances. To use Table 220.55 effectively, firstly determine the total connected load of all cooking appliances. This is simply the sum of the individual appliance ratings in kilowatts or volt amperes. Secondly, locate the appropriate row in the table based on the number of appliances. The table provides different columns for various scenarios, such as single-family dwellings, multifamily dwellings, and commercial establishments. Thirdly, read across the row to find the demand factor or demand load that corresponds to the total connected load. The demand factor is a percentage that is applied to the total connected load to determine the demand load. The demand load is the amount of power that the electrical system must be capable of supplying at any given time. Note that the notes accompanying Table 220.55 provide additional guidance and exceptions for specific situations. For example, Note 1 allows for a demand factor of 100% for the first 12 kilowatts of cooking appliance demand and 50% for the remaining demand, as we discussed. This is applicable when there are multiple cooking appliances with varying ratings. The note recognizes that not all appliances will operate at their maximum rating simultaneously. Note 2 addresses the situation where there are two or more single range units. In this case, the demand load is calculated based on the sum of the individual range ratings with a minimum demand load of 8 kilowatts. This note ensures that the electrical system is capable of supplying sufficient power to operate multiple ranges simultaneously. Note 3 provides guidance on calculating the demand load for wall-mounted ovens and counter-mounted cooking units. In this case, the demand load is calculated based on the sum of the individual unit ratings with a maximum demand load of 100% of the total connected load. This note recognizes that wall-mounted ovens and counter-mounted cooking units are typically used independently, so there is no need to apply a demand factor. Note 4, as mentioned, allows for a 100% demand factor for cooking appliances in certain situations. This is applicable when the cooking appliances are used infrequently or when the electrical system is designed to accommodate the full connected load. This note provides flexibility for designers and installers to tailor the electrical system to the specific needs of the installation. Note 5 addresses the situation where there are multiple cooking appliances with different ratings. In this case, the demand load is calculated based on the sum of the individual appliance ratings with a demand factor applied to the portion of the load that exceeds a certain threshold. This note allows for a more accurate calculation of the demand load when there is a mix of cooking appliances with varying ratings. Several factors influence the demand load calculation for cooking equipment. Firstly, the size and rating of the cooking appliances themselves. Larger appliances with higher ratings will naturally contribute more to the overall demand load. Secondly, the number of cooking appliances installed. More appliances will generally result in a higher demand load, although the demand factor may reduce this impact. Thirdly, the diversity of the cooking appliances. A mix of different types of appliances, such as ovens, cooktops, and microwave ovens, may result in a lower demand load than a set of identical appliances. Fourthly, the usage patterns of the cooking appliances. Frequent and simultaneous use of the appliances will increase the demand load, while infrequent or staggered use will decrease it. Fifthly, the applicable electrical codes and standards. These codes and standards provide guidance on calculating demand loads and ensure that the electrical system is designed to safely and reliably supply power to the cooking equipment. Understanding these factors is essential for accurately calculating the demand load for cooking equipment and ensuring the electrical system is properly sized and protected. Proper demand load calculation is crucial for several reasons. Firstly, it ensures the safety of the electrical system. An undersized electrical system can overload, leading to overheating, insulation damage, and even fires. Secondly, it ensures the reliability of the electrical system. An overloaded electrical system can experience voltage drops, causing appliances to malfunction or fail prematurely. Thirdly, it ensures compliance with electrical codes and standards. These codes and standards are designed to protect people and property from electrical hazards. Fourthly, it optimizes the efficiency of the electrical system. An accurately sized electrical system minimizes energy losses and reduces operating costs. By carefully considering the factors that influence the demand load and applying the appropriate calculation methods, you can ensure that the electrical system is properly sized and protected. Here are some practical considerations for calculating the demand load for cooking equipment. Firstly, gather all the necessary information about the cooking appliances, including their size, rating, and type. This information is typically found on the appliance nameplate or in the manufacturer's specifications. Secondly, consult the applicable electrical codes and standards, such as the National Electrical Code, to determine the appropriate calculation methods. Thirdly, consider the expected usage patterns of the cooking appliances. Will they be used frequently and simultaneously, or infrequently and staggered? Fourthly, factor in any applicable demand factors or diversity factors to account for the fact that not all appliances will operate at the maximum rating simultaneously. Fifthly, perform the necessary calculations to determine the demand load. Be sure to double-check your work to ensure accuracy. Sixthly, compare the calculated demand load to the capacity of the electrical system. Make sure that the electrical system is capable of supplying the demand load without overloading. Seventhly, consult with a qualified electrician or electrical engineer if you have any questions or concerns. They can provide expert guidance and ensure that the electrical system is properly designed and installed. By following these practical considerations, you can accurately calculate the demand load for cooking equipment and ensure that the electrical system is safe, reliable, and compliant with applicable codes and standards. Let's delve into some additional details regarding Table 220.55. The table is structured to provide demand factors based on the number of household cooking appliances. The more appliances, the lower the demand factor generally, reflecting the low probability of all appliances operating at full capacity simultaneously. Note 1 is particularly important. It allows for a reduction in the calculated load when there are multiple appliances. The 100% demand factor for the first 12 kilowatts recognizes the base load that is likely to be present. The 50% demand factor for the remaining load acknowledges that the additional appliances are less likely to be used concurrently at their maximum ratings. When applying Note 1, it is crucial to accurately determine the total connected load of all cooking appliances. This includes all ovens, cooktops, and other cooking equipment that are subject to the demand factor calculation. It's also important to understand the definition of a household cooking appliance as defined in the NEC. This will ensure that all applicable appliances are included in the calculation. In some cases, it may be necessary to consult with a qualified electrician or electrical inspector to determine whether a particular appliance is considered a household cooking appliance for the purposes of Table 220.55. Note 2 addresses the scenario where there are two or more single-range units. This is common in some dwellings where there are separate cooktops and ovens or multiple ovens. In this case, the demand load is calculated based on the sum of the individual range ratings with a minimum demand load of 8 kilowatts. This minimum demand load ensures that the electrical system is capable of supplying sufficient power to operate multiple ranges simultaneously, even if their individual ratings are relatively low. Note 3 provides guidance on calculating the demand load for wall-mounted ovens and counter-mounted cooking units. These appliances are often installed separately and may have different ratings. In this case, the demand load is calculated based on the sum of the individual unit ratings, with a maximum demand load of 100% of the total connected load. This approach recognizes that wall-mounted ovens and counter-mounted cooking units are typically used independently, so there is no need to apply a demand factor. Note 4, as previously mentioned, allows for 100% demand factor for cooking appliances in certain situations. This is applicable when the cooking appliances are used infrequently or when the electrical system is designed to accommodate the full connected load. This exception provides flexibility for designers and installers to tailor the electrical system to the specific needs of the installation. However, it is important to carefully consider the potential consequences of using a 100% demand factor. If the cooking appliances are used more frequently than anticipated, the electrical system may become overloaded. Note 5 addresses the situation where there are multiple cooking appliances with different ratings. This is common in dwellings with a mix of ovens, cooktops, and microwave ovens. In this case, the demand load is calculated based on the sum of the individual appliance ratings, with a demand factor applied to the portion of the load that exceeds a certain threshold. This approach allows for a more accurate calculation of the demand load when there is a mix of cooking appliances with varying ratings. The threshold and demand factor will vary depending on the specific circumstances. When applying Table 220.55, it is important to consider the voltage rating of the cooking appliances. The table is based on a nominal voltage of 240 volts. If the appliances are rated for a different voltage, such as 208 volts, the demand load may need to be adjusted accordingly. This adjustment can be made by multiplying the demand load by the ratio of the actual voltage to the nominal voltage. A table assumes that the cooking appliances are connected to a dedicated circuit. If the appliances are connected to a shared circuit with other loads, the demand load calculation may need to be adjusted to account for the additional loads. This adjustment can be made by adding the demand load of the other loads to the demand load of the cooking appliances. When determining the appropriate conductor size for the cooking appliance circuit, it is important to use the ampacity tables in the NEC. These tables provide the allowable ampacity for different types of conductors based on their size and insulation type. The conductor size must be large enough to carry the calculated demand load of the cooking appliances without overheating. When installing the cooking appliance circuit, it is important to follow all applicable codes and standards. This includes requirements for grounding, overcurrent protection, and wiring methods. Proper installation is essential to ensure the safety and reliability of the electrical system. In addition to Table 220.55, there are other factors that may need to be considered when calculating the demand load for cooking equipment. These factors include the type of dwelling, the size of the dwelling, and the climate. The type of dwelling can affect the demand load because different types of dwellings have different cooking habits. For example, a single-family dwelling may have a higher demand load than an apartment because the occupants of a single-family dwelling may cook more often. The size of the dwelling can affect the demand load because larger dwellings may have more cooking appliances. For example, a large house may have 2 ovens and a cooktop, while a small apartment may only have 1 range. The climate can affect the demand load because cooking habits may vary depending on the climate. For example, people in cold climates may cook more often than people in warm climates because they may want to cook warm meals to heat up their homes. When calculating the demand load for cooking equipment, it is important to consult with a qualified electrician or electrical engineer. They can help you determine the appropriate calculation methods and ensure that the electrical system is properly sized and protected. They can also provide guidance on selecting the appropriate conductors, overcurrent protection devices, and other electrical components. By working with a qualified professional, you can ensure that your electrical system is safe, reliable, and compliant with applicable codes and standards. Let's also consider some common mistakes to avoid when calculating the demand load for cooking equipment. Firstly, failing to account for all cooking appliances. It is essential to include all ovens, cooktops, and other cooking equipment in the calculation. Secondly, using the wrong demand factor. Table 220.55 provides different demand factors for different scenarios. It is important to select the correct demand factor based on the number and rating of the appliances. Thirdly, neglecting to consider the voltage rating of the appliances. The table is based on a nominal voltage of 240 volts. If the appliances are rated for a different voltage, the demand load may need to be adjusted. Fourthly, ignoring the requirements for grounding and overcurrent protection. Proper grounding and overcurrent protection are essential for safety. Fifthly, failing to consult with a qualified electrician or electrical engineer. They can provide expert guidance and ensure that the electrical system is properly designed and installed. By avoiding these common mistakes, you can ensure that the demand load calculation is accurate and that the electrical system is safe and reliable. The information presented here is for educational purposes only and should not be considered a substitute for professional advice. Always consult with a qualified electrician or electrical engineer before making any decisions about your electrical system. They can assess your specific situation and provide guidance that is tailored to your needs. Electrical work can be dangerous, and it is important to take precautions to protect yourself and others. Always disconnect power before working on electrical circuits and follow all applicable safety procedures. By taking these precautions, you can minimize the risk of electrical shock and other hazards. Remember that electrical codes and standards are constantly evolving. It is important to stay up to date on the latest requirements to ensure that your electrical system is compliant. This can be done by attending training courses, reading industry publications, and consulting with qualified professionals. By staying informed, you can ensure that your electrical system is safe, reliable, and compliant with applicable codes and standards.